A slight addendum to something I said on the show last week. If I'm to quote myself, I said GANs are under no obligation to be interpretable. And I think that's an important point here. All of this deepfake technology, all of the terrifying and wonderful things that generative adversarial networks are capable of producing, that technology relies on a complex algebraic circuit. It will definitely be the case that people build black box GANs. But one episode that really has been sticking with me lately, if you didn't catch it, be sure to go back and listen to when I spoke with Cynthia Rudin, who taught me an important lesson. It doesn't seem to be the case that a truly black box model is required. Maybe it's the easy way to do it. Maybe there's job security in that. A couple of patents or maybe some corporate bravado. Most systems are not that complicated. Certainly nature is not so cruel. So while we will never escape discussions that involve black boxes and black box techniques, what I wanted to get into today was the fact that I oversold that a little bit. Actually, there is some intersection between GANs and interpretability, more so than I'm going to cover in just a single episode, to be clear. But today I've got a great interview where we discuss some of the ways in which GANs can be controlled, influenced to do certain things, or ways in which we can understand how they're operating under the hood. GANs are trained on large corpora of data, shown many faces or maybe eventually many songs or many Word documents, and asked to produce more like that. And they accomplish that job with sometimes stunning accuracy and sometimes childlike malevolence. But these systems, even if we don't constrain them and say you must be interpretable or explainable, they still have a mechanism. They still work by a certain process. It's algorithmic. And surprisingly, it might not take much to learn a little bit about what's going on under the hood. Simple techniques like principal components analysis or PCA, when deployed in smart ways like we're going to talk about today, it seems like they might give us some great insight into what's going on under the supposed black box hood. This week on the show, I speak with Erik Härkönen about how he added some controls into that typical interface that allow you to manipulate the types of images that are produced. Erik did this work as part of an internship at Adobe, the makers of Photoshop. And maybe we don't say often enough on Data Skeptic, views of the guest don't represent blah, blah, blah. Of course, all that's true. But take for a moment and notice, Adobe, makers of Photoshop, pretty much the best thing out there, they're actively interested in this technology. That'll tell you exactly how powerful these sorts of things are going to be in our lives very soon.
My name is Erik Härkönen. I'm a master's student at the Visual Computing Group in Aalto University in Espoo, Finland. And I recently did an internship with Adobe Research, and this paper is also in collaboration with them.
Very neat. Well, Erik, to begin with, tell me a little bit about your graduate studies. What types of problems are you interested in?
Right, so I've been involved in computer graphics a lot, so physically based rendering. And recently during my internship, I also started working with generative models. So I'm still a master's student finishing up my studies, so I don't have a vast experience in the field, but I'm getting started and these are really interesting problems. So I'm eager to work on these in the future.
Well, one of the drawbacks to this being an audio podcast is that people can't enjoy some of the amazing visual aspects of your work. I will be sure to include a link to the YouTube videos in the show notes for this. But for those, maybe the visually impaired, can you give us a quick description of what are some of the, in my own opinion, rather stunning effects you can produce with the research you've been doing?
Right. So generative adversarial networks, or GANs in general, they've really skyrocketed in image quality. So we can generate human faces or other photos of landscapes or objects that can look almost photorealistic. It might be hard to realize that they're actually generated by a computer, but it's hard to control these models. So with our method, we're really giving the controls to the user to change the identity, the pose and the expression of a human face, or the apparent gender or the hairstyle, or maybe move around a car or rotate a car in a scene or move a dog around, make it bigger, smaller, change the background and the clouds in the sky and so on.
One of the first exposures I had to these ideas was when Google released Deep Dream, which I guess is sort of a primitive here. It's some of the earliest work that led in directions like this, even though I'm not sure if they used GANs or not.
That was not GAN-based.
Their results were always kind of trippy, like maybe they'd be good for a music video or something. It seems like the results we're seeing now, the state of the art, are much more photorealistic. Are you aware, are car companies using some of these technologies or anything like that you've heard of? Or do you think we're not close enough for that maybe?
I think for car commercials, commercial specifically, we're not quite yet there because the image quality expected in a commercial is super, super high. But I think for some of these more creative fields where, for example, if you're designing clothes or shoes or artwork, digital artwork, it might make sense to kind of prototype and look at new possible products or paintings or stuff like that. The image quality is really improving steadily still. So one day I can see GANs being used in stock photography and stuff like that, and maybe even in commercials.
I know you've looked at a lot of these as you've produced them, so maybe we can assume your eye is better trained than the public. Do you think you have a talent for spotting GANs, or spotting the output of GANs, I guess I should say?
There's a few giveaways. Usually, if you're looking at, for example, faces, the background is often not quite consistent or realistic, might be too simple, or there might be patterns that don't look quite right. And I think in general, practitioners in the field know how to spot some of these typical features or artifacts, but I really think a few years down the line, it's not going to be possible anymore.
So most of my experience playing around with these myself, which is somewhat limited certainly compared to your experience, but it's that the GAN I might want to use, I've trained it up or I've acquired it from somewhere, maybe extended it, and I want to transform images. It's kind of a throw of the dice for me. You know, I can tweak some things randomly, just kind of guessing and flipping weights here and there, and I'll get some interesting results, but I feel like I'm in the dark and I'm blind just reaching around. Has that historically been what style transfer and techniques like that have been like before some of the research you've been involved in was getting to?
I would say historically there's been a few different approaches to controlling generative adversarial networks. So one approach might be to just label a bunch of your training data that you feed to the model during the training phase. You're looking at your training data and you're finding some attributes that you consider to be important, and then you label your data and you tell the model, hey, please learn these things because this is what I consider to be important. And recently some research has shown that even just labeling 1% of your training data might be enough to get a model where you can change some aspects in a meaningful way. But you still have to retrain your model, which is a very costly thing to do, and also just it's very time consuming to manually label your data. And also you're kind of limited by what you expect your data set to contain. If you have some abstract data set where you're not quite sure what the important directions of change are, it might be hard to label. And then the second approach would be to take a pre-trained generator and then just hope that it has learned something interesting, and then you have a hypothesis that maybe it has learned about the pose of the head or something like that, and then you can verify this by generating a bunch of images and then labeling them and then trying to identify a direction in the input space that generates this effect. But again, you're kind of limited by your own imagination and what you can come up with, and you could even use an existing attribute detector that knows how to identify the gender or the expression in a face, but you're relying on something that someone else has made before you. So our work really just is more exploratory, and we ask the model to show us what it has learned. So we do it the other way around. Instead of verifying a hypothesis, we ask the model to show us the largest or the most important directions of change, and then from these we can extract controls. So I'd say that's really the difference. Or we're not looking for anything in particular, we're just asking the model to show us what there is, and it turns out that there's lots of interesting sliders to find in this space.
Yeah, let's break into those sliders a little bit. I, before reading the paper, didn't necessarily have a bias either way. It could have been in my mind that the ways in which the model learned things were exotic and foreign to me. I've done some principal components analysis in my past, and similar to like BERT vectors or any other embedding, they're just numbers that happen to work really well. I can't explain why it's 37 or minus 70 or whatever these numbers are. So I wasn't sure what a GAN was going to give us in that way. What did you guys find? Are there kind of human interpretable parameters in there?
Yeah, so in general, PCA orders the components it finds. It orders them by the variance that they explain. So if there's some aspect that varies a lot in the generated images, that's going to be explained by the first few principal components. And in general, we find an interesting behavior where the principal components have a style content separation in datasets where if we have a dataset where there's a lot of geometric change, that change is going to be captured by the first few components. And then the components after that, because they're orthogonal, they're not going to contain that information. And then instead, they're going to explain some other variants. So the first few components are really quite geometric. The head might be rotating, or the dog might be moving left to right or up and down or zooming. And then the later components might explain more style properties of the image. So you might get different colors or slight morphing of the geometry, but nothing as major as in the first few components.
Yeah, there's sort of a wow factor to your work I want to circle around on here and make sure listeners appreciate that we can talk about the linear algebra of all your work and, the complex mathematics, and some of the listeners will stay with us and maybe some of them won't. But at the end of the day, anyone can go into sort of a user interface like the one you guys built, and there's a slider and you go all the way to the left or all the way to the right. Anybody can do that, and you can see a pretty profound change. What's going on behind the scenes as people move that slider back and forth and see faces age and de-age in real time? What's going on under the hood there?
So the technique is based on the principal components themselves, and we find that the principal components, when we move along these components in the latent space, so the input space of the generator, we get some interesting changes in the image just by moving along these directions. But sometimes these principal components might be entangled in different concepts. So we might have a head rotation that simultaneously also slightly changes the gender of the face, or we might have, a zoom that changes the background a lot or something like that. So what we also find is that by taking these edits and then restricting their effects to only certain layers of the generator, we're kind of utilizing the hierarchical structure of the generator to get more interpretable, more disentangled edits. That's also a major contribution. We treat the generator as more of a hierarchy that can be manipulated at different points, and that's really a key to getting nice isolated edits in the image.
Yeah. Could you tell us a little bit more about that hierarchy? You were mentioning the highest valued principal components are capturing geometry and these other features. What do we find in the tail as we explore that?
So I would say there's really two hierarchies at play here. The first hierarchy is the ordering that is given by PCA, which puts the large geometric stuff in the first few components and then more style changes in the later components. So you might have a component that adds more reflections or removes reflections from the image of a car, or we might have a component that changes the color of the ground or changes the sky or something like that. And then the second hierarchy is in the network architecture itself, where we start with a very abstract low-dimensional input noise vector, and then this is transformed at the intermediate layers of the generator into an image. So this very, very abstract representation turns into something very concrete. So by looking at the activations of the generator at different layers, we can find different kinds of things. It's known from previous research that the generator on the first few layers starts by deciding the overall geometric appearance of the image. So where is the object generated? How large is it? What's its orientation? And then the middle layers, for example, in the case of a face, might decide the expression and the appearance of the eyes and the hair. And then the later layers of the generator define the colors and the shading of the image. So there's really two different orderings here at play. And by combining these two, we can get a lot of control over the image.
Do you have any sense of how sensitive results like these are to the training data set? If you brought in, photos taken from elsewhere, how well will the embeddings and these sorts of transformation techniques transfer into out-of-sample results?
Generally, editing, no matter if it's our method or supervised methods, they work based on samples that are not too exotic, too far from the mean, so outliers worse. But in general, I think using PCA might actually be an interesting way to kind of analyze models in general and compare them. So, for example, the new StarGAN 2 by NVIDIA, we've found that we can generate very nice-looking disentangled edits, and the behavior of this model seems to be very nice due to its architectural decisions. Maybe it would be interesting to actually monitor the principal components during the training of a GAN to kind of get a feeling for what it's learning and what kinds of aspects it's considering important, and maybe use that to somehow improve the models in the future.
Thanks to this week's sponsor, the Springboard Data Science Career Track. The Data Science Career Track is similar to online boot camps, but the real difference is that it's project-based. So while you're learning methodology, you're applying it and building up your portfolio. That's key. Every open position for data scientist or similar engineer, I expect a GitHub link with something on it. Every student in the program is paired with a data science expert who provides unlimited one-on-one mentorship to support your unique needs. You'll need a basic understanding of Python or another modern object-oriented programming language, and some probability and statistics. And best of all, Springboard offers a job guarantee for all their career tracks. This means you don't have to pay for the program until you secure a job in the data science space. Data Skeptic listeners have access to an exclusive offer. There are scholarships of up to $500 for eligible applicants. Make sure to enter the code DATASPRINGBOARD, all caps, no spaces, when you enroll at springboard.com. There are 20 scholarships available for students who enroll. See how to qualify and apply. It takes just 10 minutes. Take the next step in your data science career. Head over to springboard.com, and it's Data Springboard for the code. Yeah, absolutely. We've talked on it a little bit already, but explore the fact that these are interpretable features you're presenting. Could you go into a little bit of depth about how they're interpretable in this place where deep learning and all that, I didn't expect to find interpretability, I guess?
Right. The supervised edits are kind of interpretable by design, where you label your data according to some axis that you think is important. And then if you have enough data labeled, then you can find directions in the GAN that change only this one aspect that you're interested in. But in general, looking at the principal components, they might often change many things together. So really by limiting the layers, we're extracting what we think is interpretable and interesting. So we might have a direction that adds a smile and a few other things. Well, if we think that just changing the mouth is something we're interested in, and then we can just hone in on the layer that mainly controls the mouth. So there's another factor here, which is that in the supervised case where we, for example, try to find a direction in latent space that adds a smile, there's actually lots of different kinds of smiles, and there's lots of nuances here that are not really captured by one single direction. So we can find lots of different kinds of smiles and expressions in our PCA space, and really the interpretability comes from the observer. So what you think is interesting and interpretable, well, that you can discover lots of different things in these models.
Could you comment a little bit on some of the computational aspects of this? A lot of the interpretability techniques I'm familiar with, I don't want to say it's a flaw, but something to consider is that they can be computationally demanding. PCA, not necessarily as much. Do you think that gives some opportunity here that this could become more common in pipelines and training procedures and stuff like that?
Especially for the style GAN models, where we have a so-called intermediate latent space that is still quite low in dimensionality. For these models, it's very fast to run PCA. But another thing to consider is that PCA can actually be run at any of the intermediate layers of the generator. So it would certainly be interesting in the future to run PCA at other intermediate layers as well, and perhaps in other geometric configurations. So instead of considering the whole activation volume at some intermediate layer, why not consider one spatial position in isolation and so forth? Also, a limiting factor is the dimensionality of these intermediate layers. We run PCA on very early layers of the generator because that is computationally feasible. But for example, for big GAN, it gets really expensive to run PCA at some of the later layers. But I would say in general, this is still fast. We're talking minutes for style GAN and maybe a couple of hours for a big GAN layer. So this is quite accessible even for the general public. And I would say that's something I'm excited about as well. We'd love to see people use our method on all kinds of different generators and try to find different kinds of interesting knobs and tweaks. And we'd love to see what the community can find in these complex representations in GANs.
And there's the video I was mentioning, and it's showing off some software that exposes the controls so you can see the output and whatnot. And I don't know if that's just sort of a prototype you guys built to show off the work or if it's a tool that I'm unaware of, but could you comment a little bit on the underlying software there and if other users could work on that, or what's the current state of that project?
The tool that we show in the video is what we use internally to find these interesting directions of change. And the code base and everything related is also online in GitHub. So anyone can really play around with this interface. And the mathematical principles behind our project are very simple. So PCA is very well studied and there's lots of reference implementations. So that's nothing fancy. And then in the case of big GAN, we're also using linear regression to transfer these principal edit directions back to the input latent space. So in fact, it would not be very hard to recreate our tool in some other code base.
And what do you guys work on specifically for your stack?
So we're using PiTorch as the underlying framework. It's used a lot by researchers because it's easy to manipulate the models in a more dynamic way instead of the old TensorFlow way of building a static graph. And also we're using an OpenGL viewer. And interestingly, it's real time because the images generated by the GAN are displayed on the screen directly from GPU memory without going via the CPU, which is also a consideration in order to make it really fluid and interactive.
Is that run on the client through the browser, or is that a local operating system app then?
The tool is local, so the user would download it to their own computer and then play around. Additionally, we do have a Google Collaboratory notebook that can be run by anyone for free online. So it's not as responsive, not as nice to use, but it's certainly something you can use to play around if you don't have the hardware at home.
And if nothing else, a good way to get introduced to this and play around with it a little bit. So we'll have a link to that Collab Notebook in the show notes as well. Maybe it would be good to unpack a little bit more of the latent space and some of the actual transformations. We've been discussing the use of PCA in here, and certainly it's effective. Do you think that's an area of open research? Are there other dimensionality techniques that might be of interest, or would you focus efforts elsewhere in moving this forward?
I think it would be worth it to try out different kinds of matrix factorization algorithms and other kinds of dimensionality reduction. So that's something that would be very interesting. And then also running PCA in other configurations, as I mentioned before, or perhaps at later layers. So these are certainly things that would make sense. And also there's some concurrent work that does clustering on the internal activations of a GAN as well. There's still lots to be discovered in different ways to manipulate these models.
And how about in the space itself? Do you think there's much to be learned? Is this, as I described it earlier, just this mathematical space of random numbers? Or perhaps will techniques like this help us better understand the structure of that space?
I think the principal components can certainly be used to reason about what the generator has learned and how it is operating. So I think it can also help us analyze our data sets and find biases in the data set. So if, for example, the sports car versus family car, where a sports car is typically shown in an open environment and the family car is in an urban area. So these kind of things, they highlight the biases in our data sets, and we can kind of reason about what the generator has learned. So in that sense, I think this might also be useful to change our models or perhaps improve our data sets or something like that.
Earlier, you were describing the process of asking the model to show us something, which I think is pretty powerful. There's a lot of discussion about accuracy and F1 scores and all these traditional metrics, but they seem to be necessary but not sufficient, perhaps, in describing everything about our models. The ability to query the model and say something like, show me what this person would look like, but older, seems to have this really powerful interactive aspect. Do you have any thoughts on how that becomes part of the training process or the review process of a model for a machine learning engineer of the future?
I think the requirements and standards are going to rise. So far, we've really been content with having a model that produces realistic looking images. But for these models to really be useful in the future, I'm sure the community will want also to make sure that the models are somehow editable or that it's easy to interact with them. So I'm hoping that some kind of analysis like this will be included in the future as well in research papers.
And with regard to these sorts of fine-tuning and tweaking we've been describing, you outline a number of ways in which someone might go under the hood and adapt some knobs and things like that, and even build out the right controls for that. I'm curious to hear your thoughts. Do you see this as maybe a profession of its own, that there'll be a type of artist that knows how to operate this board the way a pianist operates a piano? Is that somewhere we're headed with this technology, or will someone come around and maybe give us a meta knob that does all the work all at once?
I think that's actually possible. So far, just from myself playing around with the model, I've actually learned a lot about how to interact with these models and how to best extract interesting edits. So I can totally see someone becoming an expert at a specific model. So if we have a very high quality face model, for example, I could see an artist or some other user getting to know all the ins and outs of this model and really knowing how to interact with it. So I think that's feasible, yeah.
So I imagine, well, for sure you've heard of, most listeners as well, the aspect of deepfakes, that there are people out there using technologies like this to come up with things that aren't real and present them as real. And that is sort of a looming threat. As we commented earlier, every deepfake to date seems to have a few weirdnesses about it you can tell. How far away do you believe we are from a time that this is scary, I guess? At what point do you become worried that a deepfake can be so real that it's a credible threat to information and truth?
I think it's definitely coming at some point. So it makes sense for people to kind of get accustomed to the idea that if we see something, we might not be able to trust it completely without verifying the source first, which I suppose has always been the case. So yeah, I think the deepfakes are, and in general, like images generated by machine learning models are getting super realistic, and it will definitely be hard in the future to tell what's an actual photo and what's generated by a machine learning model. That being said, traditional photo editing has been really impressive as well, as long as I can remember. So there's always been the possibility of really manipulating images and making them look like something else. So I think this is just another tool in that toolbox.
Yeah, nothing especially new, just a different technique, maybe a more efficient one.
Yeah, I would say so.
I have been reading a lot about the growing zoo of different types of GANs. So in addition to Big GAN, there's kind of this other suite of different types of GAN models out there. But do you think your techniques can be applied to those other architectures as well?
Yeah, that's an interesting point. In fact, I would say our method is not limited to GANs at all. You can run it on any machine learning model that has some internal activation layer with a non-isotropic shape. So anything that's shaped in some interesting way, you could potentially analyze with our method. And in general, one key aspect here, in order to get the disentangled per layer manipulation, you need a model where the input noise vector is fed not only into the first layer of the generator, but also all the subsequent layers. So I would say any model that has roughly the same structure would be potentially editable by our method.
And what do you see as some of the next steps in this line of research?
I would say in general, it's interesting. These techniques so far are just manipulating the outputs of GAN, so fictional photos or images generated by these models. It would also be interesting to see there's a parallel orthogonal line of research where people take real images and then represent them in the space of a GAN. So how well would these editing techniques transfer to real images then? That would be very interesting to see. And also I would like to see changes to network architecture that make these very specific interpretable edits even easier to perform. So I mentioned StyleGAN 2 before, where where the architectural decisions really make it very manipulatable. But certainly there's still some room to change the architecture in a way where we can get even more specific control of individual aspects in the image. So I would love to see GANs and machine learning models also be designed in a way where they're easier to interact with and easier to manipulate.
Very true. And I guess along those lines, it's sort of a discussion of tooling. Could you maybe share your thoughts on where all this should go? Should we be building home machines and having open source projects we install? Maybe we all work in the cloud? What do you think is the evolution of the toolkit for ML practitioners?
That's a difficult question, I must say. Like I said before, I'm just getting started on this journey of being a researcher, so I don't have a very large vision at this point. But I would say these techniques are very exciting and the results speak for themselves. So there is some concern about the growing need for data in order to train these models. So I would still like to see research published that researchers can actually reproduce instead of just the big companies training huge models that are completely out of reach from the normal hobbyist or practitioner.
Yes, it's a good point. And open source though they may be, their size makes them impractical much of the time.
Yeah, exactly.
Yeah, it's certainly interesting times we're in. Erik, where can people follow you online?
I don't have a strong media presence yet or internet presence yet, but I can be found on Twitter under the tag Harskish, and also my GitHub would be a good place to look. So I have lots of projects there that are open source, and hopefully I'll be adding to that collection of projects in the future.
Absolutely. Well, if you tweet a few images or videos of these GitHub projects, you'll have a pretty strong social media following quick, I imagine. This is neat stuff. I want to encourage all the listeners to go check out the links in the show notes, watch the video, see the collab and all that. Erik, thank you so much for coming on and sharing your work.
Thanks a lot for having me.
Thanks for listening to Data Skeptic Interpretability. Our guest this week was Erik Härkönen. Our theme song is Number 5 by the Third Wave Goat, Big D and the Kids Table. Claudia Armbruster is our associate producer. Guest coordination by Vanessa Burciaga. I'm your host, Kyle Polich. Here in Los Angeles, we're undergoing a surge in infection. It's a time for us to stay indoors. If you're the same, I hope you're doing that also. The time series data tells a very simple story.